Hi everyone, in this video we are going over implementing Hill Cipher in Python. This video complements the introduction video to Hill Cipher where we went over the definition of Hill Cipher and saw an example of Hill Cipher. The example we see in today's video is the same as the one we went over. So if you have already watched the explanation to Hill Cipher and you'd like to know how you can implement it in Python, then just sit back and enjoy this video. If you're already familiar with Hill Cipher and would like to know how you can implement it in Python, then you're already in the right place, but I suggest looking over at the other video just so you can familiarize yourself with the plaintext and the key and in general the setup we are using. All in all, I hope you enjoyed this video and learned something new. So we are getting started with the implementation in Python at this moment. First things first, we need to import the NumPy package in Python because we are dealing with matrices, and NumPy has made it easy to work with matrices in Python. Then we need to define our plaintext, which is the word Hill Cipher. And as we've seen before in other videos, we can remove white space. Usually it's customary or it's the norm to remove white spaces wherever possible when we'd like to encrypt a message. And we can also make everything lowercase, so just to be consistent. And we are going to display it here to make sure everything works as intended. The key that we used is the word test, and just going to display it here. And there are some Python commands that it's nice to be familiar with when we are working with characters. So the chr command is a command that takes as an input an integer and returns the corresponding character in the ASCII table. So 97 is the number that corresponds to lowercase a, and the OR command is the command that reverse this operation. So OR A actually will give us 97, and the reason we don't need to be familiar with both of them. I'm just going to use the chr command for what comes next. But in general, when we're working with characters in Python, especially in regards to encryption, it is nice to be familiar with these two commands. Next, we need to have a mapping, define a mapping between English alphabet and numbers in mod 26. And we are going to define a variable called EAM. The reason I call it EAM because it stands for English alphabet mapping. You can call it any other name as you wish. And we are taking a dictionary approach, chr of I. So there's an integer that goes in. We are going to subtract. So we are going to assign a number in mod 26. That's why we are going to subtract 97 from it for I in range of. We are starting from 97, and there are 26 letters in English alphabet. That's why we are adding 26. So if you're using with a different in a different language, or for any other purposes, you have more than 26 or less than 26, you adjust it according to that language. But for English and for our purposes, 26 is what we're looking for. And we can see what's happening. Letter A is being mapped to number 0, B to 1, and so on and so forth as expected. And it's nice to have the reverse of this dictionary. So we want to switch the place of the key and its value. There are multiple ways to achieve this in Python. I just like to interchange the uh, places of the key and value, and that should do it for us. And I call it EAM REV for reverse. It's nicer to print it so it doesn't take as much space. And as expected, number 0 corresponds to letter A, 1 corresponds to B, and goes on until 25 for Z. Next, we need to map our plain text and the key that we have to numbers in mod 26. And for this reason, we can for this goal, we can simply use list comprehension in Python for I in the plain text. So EAM is the dictionary that takes as an input a letter in English alphabet. For example, EAM of A should give us 0. So EAM I for letters in the plain text, these are the corresponding numbers in mod 26 for that plain text. And we can call this PT numbers or anything else as you wish. Same idea for the key. So we're gonna call this key numbers. And again, we are going to use the English alphabet mapping I for I in the key. Display to make sure everything works fine. And yes, as I remember, if I remember correctly, I should say the elements for the key are numbers 19, 4, 18, and 19. Now, because Hill Cipher, in Hill Cipher, we divide our plain text and we define our we divide our plain text into blocks, and our key is a matrix, so we need to transform the plain text into blocks and our key into a matrix. So first and foremost, there is actually a nice way to reshape our key into a matrix. So first of all, to do that, let's call this the key matrix. And first and foremost, we need to transform the list key numbers into a NumPy array. And then we can simply use the reshape command, passing the size or the shape that we are interested 2 by 2 matrix, and we can display it here. My apologies, this should be key matrix, and that is what we're looking for. Now, to take a more systematic approach, suppose we are interested in number n, right? The number of the block size, I must say. So, or the block length. We can, for this reason, we can create a new variable. We call it BL for block length, and it's gonna be the length of the key number list. So these are the elements of the matrix which were saved as a list, and in this case, because it's a 2 by RM, so the size of a block is a 2. We divide, we are interested in the quotient of this number when we are dividing it by 2. And of course, the answer is 2, but we just have to make sure of that. Yeah. And we can simply update these values to BL. So just to recap, this double backslash operation that we see here is giving us the quotient when we're dividing two numbers. So for example, if I do 5, 2, we get number 2 because when we divide 5 by 2, the quotient is number 2. And the benefit of doing that is that it would give us an integer, whereas let's say we had 4 divided by 2, this is no longer an integer. So, and when we pass this number into the reshape, we would get an error because the reshape command in NumPy cannot take integers as input, just to show you. And you can see that we get an error. The reason why is that we are giving it a float instead of integers. So that's an important distinction. Next, we need to divide our plaintext into blocks of 2. So each block would have 2 characters in them. So first we create a PT array. We have a list at first, but we have to change it to an array, NumPy array in Python, which is done with the following commands: printing it, making sure everything goes fine. And next, we need to divide it as mentioned. So there is a NumPy command that will allow you to split the array, but you can't pass the size of the array you're looking for. So if you're looking for the size 2, I couldn't or I'm not aware of a command that would allow you to do that by passing number 2. It would give you 2 blocks of characters, but instead you can divide the whole length by the number that would give you the length of the block you are interested in. So I can show you what I mean. We use the np split command. We're passing our array that we'd like to split, and here if I pass in number 2, I'm getting 2 arrays with 5 elements each, but that's not what I want. I like to get 5 arrays with 2 elements each. So instead of number 2, if I pass in number 5, we get 5 arrays, each having length 2. So again, we can achieve this for instance if we do len pt array, and we like to get we divide by 2, which should give us what we want. So len pt is 10 and bl is 2. That's why we're getting 5, which is what we wanted. So this gives you another systematic approach. Instead of passing a number, you can just passing these variables, which will take care of that part. And we save this in another variable. Let's call it pt blocks. and we can display it again once more to make sure everything works fine. For example, if I'm looking at the first element of this array, we get 7 and 8 as expected. Now we are getting ready to find the ciphertext at this point. To show you one example, we want to multiply this first block by the key matrix that we have. So this can be done with the matmul command in Python. I believe that stands for matrix multiplication. So pt blocks 0 and the key matrix. So this will give us the values of the matrix multiplication, but we are interested in these values mod 26, which we can get easily by just using the mod command. So that's very nice. And we want to do it for every block in the plaintext. So we can create another variable ct blocks, I must call it, just to be consistent. Again, using a least comprehension, np matmul pt blocks I. So this is gonna be the index of the block, and we are going to multiply it by the key matrix, so this will remain constant. We are interested in the values mod 26, and we are interested for I in range of it's actually the length of the PT blocks. So that must work, hopefully, and we can display the results. And as you can see, we get 5 blocks. Each block have length 2. So at least from a logical point of view, everything makes sense. And hopefully these should correspond to the ciphertext that we got in the other video, and we can compare the result. So to make the ciphertext and get the ciphertext and put it in a nice form, we can concatenate these values and then put it in the string. So first we can simply use the np concatenate command from Python, pass in the array that we'd like to concatenate, and then we're going to see the result in a second. And yeah, so that makes sense. We are getting the same blocks as a new array with the same elements that we see in these blocks, 17, 24, 17, 19, and so on and so forth in here. And lastly, we'd like to transform these values to English alphabet. So here we can make a new variable called city for ciphertext using a least comprehension. Now here we use the reverse of the English mapping alphabet, and in each iteration we are passing a member of the ciphertext array. For I in range of length of CT array, and we can display it, and we get the following values. And we can even make it look nicer, concatenate all of these values by the following command in Python. We can just simply join and pass in the list that we have, and there we go. We get a ciphertext, as we can see on the screen. This ciphertext, if I recall correctly, it corresponds to the ciphertext that we got in the other video. So now at this point, we've covered half of what we wanted. We wanted to show how we can encrypt and also decrypt. So at this point, we can work on the decryption component of the Hill cipher. So given the ciphertext that we see and the key matrix that we have, how can we get the same plaintext back again? So just to remind ourselves, like I'm going to display the key matrix that we have. And now we have to find the inverse of this matrix. I am going to post another video where I go more in details about how we can do it in Python. Unfortunately, as far as I know, Python does not make it easy to find inverses of matrices over finite rings. So for example, over mod 26, there is not a built-in method to find that, but there are ways to get around that. I'm going over that part more quickly in this video because that's not the main purpose, but there is going to be another video where I cover that more in details. So to do that, actually you can see it for yourself really quickly here. If np lean algebra command in the numpy package is what we are interested in working with when we are working with matrices. And the inv command for inverse will give us the inverse of this matrix. So you can see the values that we get, they are not integers. So right here, we can be sure that this is not the correct matrix. This is not the matrix that we're looking for. However, it does give us the determinant of this matrix correctly as we expect. So that's not a problem. But there is still a problem. The problem is that the value of the determinant is 289. Exactly, that's an integer value. The value of the determinant of this matrix is 289. There are no more zeros, and you can see a 6 at the end. That is not the correct value. There is precision error and things that are going on in the background we may not be that familiar with, and that's why we see that value, and that is going to cause a problem if we don't take care of it. So first we need to round this value. Make sure to not use the int command here. You can actually, let me just copy this. You can use this command, pass a float into the integer function and get this value, but keep in mind, for example, if I pass in 288.999, which is close to 289, it's not giving you 289 as you might expect. So it is just rounding it down. The correct way to do this is to use the round function. So here, if we pass in 28999, it will give us 289 as one would expect. So here we want to round this to make sure that we are getting it. So this will give us an integer value. And in the next part, we need to find the adjugate of the key matrix. And I'm just actually going to call it adjugate of the key matrix. And to find the adjugate of the key matrix, this is how we're going to do it. We're going to find the inverse that we saw before. So this here, which is not the correct value, but we can use that information to find the adjugate. I will explain it why this works in a separate video. But for now, we can just use this and take my word for it. Linear algebra dot determinant. key matrix. So we are multiplying it by the determinant matrix. And yeah, I believe that should be what we need for finding the adjugate of the key matrix. And there we go. Now we have a matrix with integer values, and that's the adjugate matrix of the key matrix that we started with. And now at this point, to find the inverse of the key, there's still one more element that we need, and that's the inverse of the determinant of the matrix. So the determinant of the matrix we calculated to be 289. 289, it's not necessary that we find the value in mod 26. The value that it's congruent to in mod 26, which is number 3. We can also just simply use the power function, the built-in power function in Python, pass in 289. We are interested in the inverse of this element in Z26. So that's why we can just number 289, the inverse of that element is number 9. If we pass in number 3, we should get the same value. I'm just gonna show it here for the purpose of demonstration. We get number 9, and that agrees with the result that we got previously. 9 times 3 is 27. 27 mod 26 is equal to 1. So that works fine. So now we are at the stage that we can actually compute the inverse of the key matrix. And for that, we can simply multiply number 9, which is the inverse of the determinant, times the adjugate of the key matrix. And we are interested in these values mod 26, so between 0 and 25. And there we go. This is another matrix that we get with elements 15, 16, 20, and 15. Again, at least from the logical point of view, it makes sense. We have 15 in the first and the fourth element, so same value as like the key matrix where the first and the last element were equal. Here we see the key for the inverse of the key, they are equal. So logically that makes sense, and hopefully it is actually the correct value, as we will see. So now that we found the inverse of the key matrix, we can go ahead and try to find the plaintext. At the moment, the information that we have is this string, or each character in a list of the same string. That's the information that we have, and we want to use this information to get to the plaintext. So we need to again, we assume that we have these values in mod 26. Actually, we can just get that real quickly again. CT numbers is so EAMI for I in CT. So these are the corresponding values in mod 26 of the ciphertext. And now we transform it into a NumPy array in Python. np.array array, and pass in the list that we have. Printing, displaying it, making sure we have the correct values. And now we're gonna split this again. CT blocks. So these are very similar to the encryption component. That's why I'm going a little bit faster over them. Pass in the array, the ciphertext array, and we are going to divide it by divide the length of the list that contains the ciphertext values in mod 26 by the block length, which is basically it's going to give us 10 divided by 2, or the quotient of 10 when dividing it by 2, which is number 5, which will give us 5 blocks indeed, with 2 elements each, which is what we want. Now that we've got to this point, we are pretty much ready to find the plaintext. So we can get the plaintext in blocks. So plaintext blocks. Again, we are assuming that we don't have this knowledge, right? Of course, we do have this information, but we are pretending that we only had the ciphertext and the key. So we define a new variable. It's not new, but we pretend it's new. Again, matmul ct blocks, the blocks of the ciphertext, and we are going to multiply this by the key inverse. We are interested in these values mod 26 for I in range of length of the CT blocks, and hopefully this will give us the plaintext in blocks, so that the values that we get they do make sense. Again, we can concatenate these values and get one list, one array instead of 5 arrays. Call this pt array. Use the concatenate function in Python from NumPy package, and pt array. And there we go. We have our plaintext in values not mod 26. One thing I like to point out at this point is that, well, the type command usually gives you the type of a variable. So for example, if I give it pt array, it tells us that this is a NumPy array. Now if I give it the 0th element of this array, we see that it returns a float, but these numbers are technically integers. So again, that's something to be conscious about, because in theory we should be dealing with integers. So there are certain places that where you pass in a float, the Python might give you an error if it's expecting an integer, and that is one of the things that might happen actually, as you'll see in a second, using a list comprehension. So if I pass in EAMI for I in pt array, oh, we got an error. Why? Because these values, the dictionary that we use for EAM, they are expected to be integers as an input. Sorry, actually, I must have, this is my mistake. I should have used the reverse, but still we get an error. Why? Because it was expecting an integer, but it's getting a number. This is definitely not an integer because of this 455 at the end. So again, we can use the round function to be safe. Even though I've given you the instruction with the round function, I still like to warn you to be very careful when you're using this approach, when you're using the round function, especially for larger matrices. Just be careful and be conscious that the system or Python may work unexpected. So just have that in the back of your mind, and check your work before applying it for important applications or uses, whatever might be the case. So just have that in the back of your mind. Now this should work fine, and we can see letters that we get in English alphabet, they are as expected, and we can put this in a new um, new list. We just call it, let's say, PT list, PT list, and display it, making sure everything works fine. And we can concatenate everything and see it in a nice form like this. And there we go. We get our plaintext Hill Cipher back again. That assures us that the method we use to find the inverse of the key works fine. The ciphertext that we found was also fine because the chances are if you found the wrong ciphertext or you had to use the wrong key or the inverse of the key, you would face problems. So the fact that we got the plaintext back, it's a reassurance that what we've done is correct. And with this, we are coming to the end of this video. I hope you've enjoyed watching this video, learned something new about Python or NumPy array, how to find the inverse of a matrix over a finite ring. And I hope to hear more from you, your feedback, your thoughts, your suggestions, what you like to see more of. I appreciate and thank you for your time for watching this video. Thank you, and until next time, bye for now.